As I promised in class, I'm going to present now a slightly cleaner derivation of the energy stored in the magnetic field of an inductor. And we're going to start by calculating the amount of work that is done on an individual electron divided by the charge of that electron. And that, by definition, is just the negative EMF. If we multiply the negative EMF by I, we're essentially taking dWe divided by QE, and we're multiplying it by the current, which is the number of electrons multiplied by the charge of electrons divided by dt. So this is the total charge divided by the current. The QE's cancel out, and we're left with the number of electrons times dWe dt, which is the time derivative of the work done per electron, and that of course gives us the time derivative of the total work done on all of the electrons. So we now have this expression that the time derivative of the total work done on all of the electrons is equal to negative epsilon I, and we know the relationship that the self-inductance times di dt is equal to the negative EMF, so we're just going to substitute that in, and so we get that the time derivative of the work done on all the electrons is L di dt times I. Okay. Now our goal at this point is to calculate how much work needed to be done to take our inductor from a current of 0 to some final current value. And in order to calculate the total work, we're going to need to integrate the derivative. And so we have the integral of dw dt, and that's going to be equal to, we substitute in this formula right here, and the inductance can go out of the integral since it's a constant. So we get L times the integral of I times di dt times dt. And this, we can do a change of variables. This is equivalent, rather than integrating over time as an intermediate variable, we can write this as just the integral of the current itself from current equals 0 to current equals IF. You can think of a way of going from here to here as these two dt's cancel, leaving us with I di, but that also changes the bounds of the integral from being time bounds to current bounds. And this is an easy integral. This is just the integral of x dx, which is x squared over 2. Of course, we're multiplying by L, so we ultimately get Li squared over 2, evaluated from the final current to 0, and that, of course, is just equal to Li final squared divided by 2. And so the work needed to take our inductor from I equals 0 to IF is given by this expression, Li squared over 2, and that's equivalent to the energy stored in the B field. I'm going to drop this subscript F going forward, but just bear in mind that what we're talking about is the final current that is going through the inductor, and that this formula gives us the work that was necessary to get to that point, and therefore the energy that is stored in the B field. Now, that formula applies specifically to line currents, but we can further generalize this to surface and volume currents. And recall that the definition of the flux is the inductance times the current. And so if we have this formula over here that work equals 1/2 Li squared, we can substitute the flux in and write that as work equals 1/2 I times the flux. And the flux, by definition, is the integral of the magnetic field over a surface area. And we know that the definition of a magnetic field, or rather the relationship to derive a magnetic field from vector potential, is that the magnetic field is just the curl of the vector potential. So we're just substituting that into this equation. But now we have this integral here. We can apply Stokes' theorem and rewrite this as a line integral around the boundaries of that surface area that we were calculating of A dotted with dl. And so our formula, we went from work equals 1/2 I times the flux, and that's equal to 1/2 I times the integral of A dot dl. Now, dl is a small vector increment that is pointing along the same direction as I. So you could also write this as 1/2 times the line integral of the vector potential dotted with the current over some small scalar step dl around the path of that current. More generally, and this is the big point, is we can take this formula for the work related to the line current, and we can write it in terms of a volume integral of the dot product between the vector potential and a current density, J, integrated over the volume d tau. And so this is the more general statement of that formula. But we can take this derivation further. First of all, we know that the current density is equal to 1 over mu naught del cross B. And we get that from, well, a slightly different formula, that del cross B equals mu naught J. That's one of the Maxwell equations, or really the early version of the Maxwell's equation that we've been using in this class. And so if we substitute this into this formula here, we get that work is equal to 1 over 2 mu naught times the volume integral of the vector potential dotted with the curl of the B field integrated over volume. So that is the formula that we're at now. But we have an identity, and I made this identity a little bit confusing in my lecture on Wednesday's class, but it turns out that I don't need to use A and B as substitutes. I'm actually going to use them to mean what they mean up here. But this is an identity that we have in the textbook from the early chapters of Griffith, the math prerequisites. We know that that del dotted with A cross B is actually equal to B dotted with del cross A minus A dotted with del cross B. So that's the identity. And we can rearrange this by basically adding the A dotted with del cross B to this side and then subtracting this over to here. And we get that A dot del cross B is equal to B dot del cross A minus del dot A cross B. And now we recognize that the curl of the vector potential is just the magnetic field again. And so what we actually get ultimately is the B field dotted with itself minus del dotted with A cross B. And so we can now go and integrate this expression and rewrite it as the integral of B dot B minus del dot A cross B dt. And we can then use Stokes' theorem to rewrite this part of the integral as being a surface integral of A cross B dotted with dA. That's just Stokes' theorem. And this is just a scalar, or rather it's a scalar product of a vector with itself. So we get ultimately the integral of B squared dt. And this really takes us to the last step of the derivation, because we have a volume integral and a surface integral. And here's the key part. If we're looking at a finite volume, this formula is an exact formula. We're done. But if we want to look at the total energy stored, we want to take this volume and we want to expand it out to infinity. Now, as we grow the volume, this integral is going to get larger but converge, whereas the surface integral, the values of A and B are going to get smaller and smaller and smaller, and this integral is going to vanish. Therefore, what we're left with in the end is that the total work done is equal to 1 over 2 mu naught times the integral of B squared d tau integrated over all space. And so that's the formula of the total energy stored in a B field, regardless of whether it's a line current, a surface current, or a volume current. And as we discussed in class, this formula is, it makes for a nice symmetry with the epsilon naught over 2 integral of E squared d tau over all space for the energy stored in an E field. So we have a really nice symmetry in those two formulas, and there you have it.